Okay, good afternoon, everyone, and welcome to the 2DCC webinar series. Today we have Mr. Riju Banerjee, who is a PhD candidate in physics, and today he's going to be talking about extreme straintronics of graphene. Mr. Banerjee?
Thank you, Kevin, and thank you everyone for being here. As Kevin said, I am a PhD student here in physics, and what I'll be talking about here is what has been the main focus of my research as a PhD student, which is extreme straintronics in graphene. So one of the most fundamental properties of matter is the measure of how it deforms under applied stress. And after studying bulk materials, elastic properties of bulk materials for past several centuries, in 2004, when graphene was discovered, it immediately opened the door for many important and interesting questions. Questions which are at the same time fundamental to understand and very important from the engineering and application point of view. For example, like how are deformations in materials which are only a single atom thick different from materials which are bulk? Then we know that traditional materials, like for example silicon, would break when you put a strain of the order of magnitude of few percent. However, graphene can sustain extreme strains over 20%. So a natural question is, how do materials behave under such extreme strain conditions which are impossible to apply in traditional materials? Then these 2D films, they are like the thinnest possible materials. So you can imagine that any stress you put on it is going to result in a huge deformation. In fact, these deformations can be so large that they can start affecting how electrons move in these materials. So you can tune electrical properties by tuning mechanical properties. So a natural question is that can we engineer some novel electronic properties which you cannot do in traditional materials by strain engineering? Then another question can be, if you think of graphene sheet as a piece of cloth or fabric, then the length scale over which the strain changes as the cloth ripples, generally that length scale is like the order of length scale of the wavelength of the ripples. And at that length scale, the individual thickness of the threads doesn't matter. And so you can easily treat a cloth as a continuous material. However, if you make the length scale of strain variations smaller and smaller and smaller, at some point, we know that the graphene is like a discrete lattice. It's not continuous material. So the question is, how are ripples in a discrete lattice different from those in a continuous fabric? So you can imagine that lists like this can easily go on and on and on, but I'll truncate it here to keep it short and just say that the main goal of my research and the talk today that I'm giving is to try to find answers to questions like these. Now, if you stare at these questions for a while, sort of the game plan of what we want to do, need to do emerges. What we need is, we need to take graphene. We can, in principle, take any 2D material, but let's take graphene because it's the most widely studied material. And it's like the poster boy of 2D materials. Then we need to apply extreme strain, which is, what is extreme strain? Strain of the order of magnitude, which is impossible to apply in traditional materials. Then to understand how a discrete lattice behaves, we need to vary it at the nanoscale. Such a strain has to be applied. And then not only we need to do this, the resultant effects also needs to be proved. Because if you cannot prove it, then there's no point in doing it. Now, if you look at it a little bit, you realize that this is a rather non-trivial thing to do at that length scale. So we start out by looking at what other people do. So the traditional method of straining a material is to sandwich a sample between two bits of diamond, apply hydraulic pressure, and then try and squeeze the hell out of it. So there are a couple of problems with this. Firstly, you can imagine if this sample is only a single atom thick, then it's very difficult to strain it, because if you just press a piece of cloth, it doesn't do much. What you need to do is take a piece of cloth and shear it tensilely, The second thing is this entire thing, though blown up here, this entire thing is like a couple of centimeters large. So if you want to probe what happens at the atomic length scale, ideally that's what you want to do, there's no way you can squeeze a large microscope in this region. So this method is either difficult or in some cases impossible. Instead, our approach is to do something very different. We grow graphene on a copper substrate with large step edges, large in the sense 35 nanometers. As graphene grows on this kind of a substrate, these are the step edges, what happens is just like a tablecloth drapes down over a tablecloth, graphene drapes down over copper step edges. And as it drapes down, it is held at the top by the van der Waals forces of the copper, and it's pulled again by the van der Waals forces of the bottom terrace. And as these two forces pull the graphene, it gets rippled. So this is what becomes our laboratory. So here is an artistic impression of the same thing. This is a copper step edge, and the graphene is draping over it, forming ripples. And of course, the graphene lattice is blown up for clarity. Now, since this happens in a flat region, we can now use the available techniques like scanning probe microscopy to study how the deformations and how to probe and image the deformations down to the atomic scale. So we'll be using a scanning tiny microscopy. Before we talk about graphene in detail, let's look at STM a little bit. So in an STM, what we do is that we bring an atomically sharp tip very close to a surface, about an angstrom distance away, and apply a voltage between the tip and the sample. Due to the voltage, a tiny current tunnels through from the tip to the sample. And as we scan the tip, we try to maintain a constant current. Now, as this current is the tunneling current, it is extremely sensitive to the distance between the tip and the sample. So the current goes down exponentially as the z height of the tip moves, z height of the tip increases. And an angstrom change in z gives an order of magnitude in I, typically. And so this is what gives STM its incredible resolution power, that we can see atoms. This is how an STM looks like in reality. This is the STM sitting downstairs in this building in the basement. And to understand how the current flows, we consider the density of states of the sample and the tip. So imagine that the sample has some density of states, and for the tip, we typically choose a material which has a flat density of states, typically boring, so that it doesn't disturb what we are trying to measure. Then as we apply a voltage, then the electrons from the tip hop on, tunnel through into the sample, and the total current is an integral of the local density of states. The local density of states is like the measure of how many electrons are living at each energy under the tip at each point. So what we generally want to measure is the local density of states. So then that can be extracted from this kind of an equation just by taking a derivative. So we'll use this extensively as DIDV measurements. So generally people will say that STM can see atoms, but what STM really sees is electron density. It's sensitive to electron density. But as electrons tend to club and live near atoms, an STM can image atoms. So what we do is, as we scan the tip, we note each x and y, the coordinate of each point, and then at each point we record how z needs to change to keep I constant at that point. And then by running a feedback loop on I, and that's how we record. So this is an image of an STM image topography of a graphene lattice. You can see the hexagonal lattice. And if you measure the DIDV, we stop at each point, change the voltage and measure the resultant current. Then this is how it looks like. So it is V-shaped, which is remnant of the Dirac cone in graphene. Okay, now let us talk about the mechanical properties of graphene. Now, because STM's ability to image nanoscale deformations and electronic properties, it has been used previously to study strain graphene. So here are some of the interesting works in this field. And you can see that people have tried a lot of things, from like accidental cases where people have found nanobubbles, thermal wrinkling, or just some random ripple lying on the surface, to actually using something like a MEMS device or substrate patterning in these cases. Interestingly, these guys see something called a pseudomagnetic field, which I'll talk about later. Now, experimental strain manipulation of graphene is still in its infancy, mainly because of two things. One is wrinkling, rippling, this is inherently somewhat messy. And secondly, because engineering anything at the nanometer length scale is really, really hard. So what we want to do ideally is, it's like, for example, if you want to know the elastic properties of a piece of cloth, you don't just look at a piece of cloth that you happen to find somewhere lying around. You pick it up, you stress it, strain it, vary different parameters like of the ripples, like wavelength, amplitude, local curvature of the ripples. And then you try to relate how these different varying parameters are related to each other. And then you try to understand what is happening. So that is what I want to talk about today. So how do you create step edges in graphene? So this was a paper that came out last year in the PRL. And they said they explored why do copper step edges or any metal step edges, they bunch together when growing in a CVD. So this is the essence of the argument, that imagine that you have a copper step edge and you have two copper step edges, each short heights, and the graphene is draping over them. Now at high temperatures when graphene grows, at those high temperatures the copper is not really a solid anymore. It can diffuse, it can flow. And as it can flow, what graphene does is, as it bends 4 times, so if there are two step edges, it bends 4 times. And there is always a cost associated with bending. So what graphene does, it doesn't want to bend. So what it does is that it pushes the copper and forming larger step edges. So large few step edges is a more energetically favorable configuration than many short step edges. So this is what drives step bunching. And this is an example from this paper where they have shown they take bare copper and on a patch they grow graphene. And as they cool down, they see that there are more step edges that form on the graphene than on the bare copper. And we were very lucky that such samples could be grown by Tommy. So if you want more information about how to grow these samples, I would suggest you talk to him, because these were the magic hands that made this work. Science is all about magic hands. You have to be fair. Okay, now let's look at what kind of strain we have. So this is, so to measure what kind of strain magnitudes we see, we image the graphene lattice and take a Fourier transform. So this is a Fourier transform of the topography, atomic scale topography of the graphene lattice taken in a region where there is no strain. And you will see this is the hexagonal lattice corresponding to the hexagon. There are 6 peaks, and this corresponds to the hexagonal lattice of the graphene. They're all equal, all the 6 peaks are equally placed because they fall on this dotted circle, so as you would expect for a strained lattice, unstrained lattice. However, if it images the atoms here and then take a Fourier transform, we see that then these peaks, they now start deviating because the lattice is distorted. And by measuring how much they have deviated from this dotted circle, we can measure that the strain is really more than 10%, which is impossible to apply in a traditional material. Later, I'll also talk about some first principle calculations that has been done, and this number is also consistent with what they find. Okay, now that we have extreme strain, graphene rippled under extreme strain, let us look at what it happens. What does classical fabric do? So if you have a classical fabric, then there are really 2 ways of inducing ripples. One is you can directly apply a compressive stress, which happens when you pinch your skin, like here. In this case, the wavelength is inversely proportional to the amplitude, because if you push it in, then the material bubbles up. On the other hand, if the other way of inducing ripples is to take a piece of cloth and then just pull it. So as you pull it in one direction, in the perpendicular direction, the material has a piezo compression, and this piezo compression induces ripples. And in this case, the wavelength is proportional to the amplitude. Now let us see what happens to graphene. How does it behave? So the first thing we did was to take topographies like this and start taking line cuts to where the ripples fall. So if you look at this line cut, you see that in regions where there is low curvature, in a straight region, there are less ripples. In a region where there is more curvature, there are more ripples. So we stared at this for a while, and then we realized that this is exactly like ripping of a tablecloth, which has more ripples at the corners, corners are the regions where there is more curvature. And that forms simply because there is more expandable material there. So graphene is just like a graphene tablecloth. However, not everything is like a tablecloth. So the first surprise came when we started taking line cuts perpendicular to the step edge. So first of all, this is the typical line cut profile. You will see that it is clearly dominated by forces other than gravity, and instead of hanging like a catenary, it drapes straight down. But what was very surprising is that this draping angle shown here, that is always conserved to be 35 degrees, irrespective of the step height, curvature, amplitude of the ripples, sheet width, anything. And so here you can see the step height varies by an order of magnitude, and that angle doesn't change. The next surprise came when we started taking line cuts parallel to the step edge. So if you extract a profile like this, this is how it looks. It's like a triangular wave. What was very surprising was that this vertex angle is always conserved to be 168 degrees. So you can see the ripple wavelength changes by an order of magnitude, and that angle doesn't change. So this is the standard deviation of this is like 2 degrees. So that means that graphene somehow behaves like a bizarre fabric that no matter how you pull it, it always buckles the same way. So now, next thing is, if you imagine that if the vertex angle is conserved, that means the wavelength is proportional to the amplitude, because the more you spread it out, the more higher it has to go, if the vertex angle is conserved. That means we must be in this region. So let's test if that is true. So if you have a classical fabric that is rippling like under a tensile stress, the sheet width L is proportional to square of the wavelength. I'll not derive this, but I'll try to motivate it by a picture. So these are two concentric cylinders with a plastic wrap draped over it. You will notice that the wavelength on the right-hand side is smaller than what it is on the left-hand side. But to sustain the larger wavelength ripples, the sheet has to drape diagonally down to increase L. So let us see if this is true for graphene. So to test this, what we do is we take two sets of line cuts in two regions on a step edge. The wavelength of the ripple in region B is twice of what it is in A. So that is shown here. The wavelength is twice. So classically, we would expect that the sheet width to be 4 times. And that is clearly not the case here. So LV is not 4 times LV. So this is something weird is happening. Now, if you think about it, in some sense, you would expect it, because a classical theory would assume that the material has some finite thickness, and it is also a continuous material. In our case, none of those hold. It is the thinnest possible material, just an atom thick. And secondly, the length scale over which strain varies is really like few nanometers. So it's comparable to the lattice constant of graphene. So it cannot be assumed as a continuous material. Next, let us look at some electronic properties. So ever since graphene was shown to have very high electronic mobility, it has always been very attractive for making electronics. And here are some of the techniques that people have tried to influence the behavior of electrons in graphene. One is by functionalizing it by dopants. So this is an individual nitrogen atom embedded in a graphene lattice. And depending on how far you are, this X points, the DI/dV measurements show that the electronic density of states change. Another method is by stacking graphene with other materials like atomic Lego blocks. And so the idea here is that electrons in one layer can affect the electrons in the other layers. So here is a cross-sectional TM of a graphene hexagon boron nitride stack. Another method that people have done is using lateral heterostructures, where at the interface of different materials, some interesting electronic properties can emerge. So here is, people have tried making transistors out of graphene interface with MOS2. And here is another one where graphene is interfaced with hexagonal boron nitride. So this is just to give a flavor. And I apologize if your favorite way of engineering, electronic engineering of graphene is not here. But this is, as I said, just to give a flavor of what some people have done. But I will relate to these second two techniques later in my talk a little bit. So what is electronics? What do we want to do? What we want to do in electronics is we want to manipulate electrons by precisely applying electric and magnetic fields. And how precisely we want to apply them and manipulate them? We want to, ideally down to atomic scale. Why not? Let's be ambitious. And now, of course, we cannot. That's why we're here. So, for example, not everything we can do. There's no reason for us to be limited by the limits of traditional electronics when we are designing the next generation of electronics. For example, many present-day electronics in our pockets around us, they predominantly use electric fields to move electrons. Generally, magnetic fields are rarely used because they're very hard to design in devices. For example, consider this kind of a profile. So there are, imagine a magnetic field profile, which is varying at the nanoscale, like it's oscillating. So, and the strength of the field is, say, decent, plus minus 10 Tesla. Such a profile is simply impossible to create using traditional electronics. Because the large fields that we create, like an MRI machine, they require really heavy machining, the size of a room. And there's no way that we can induce so much spatial variation. Because, on the other hand, if we can make non-uniform varying fields, then they are, by taking magnetic pads, then they're really weak. There is no way of making this kind of a thing. What I'll show today is this kind of a strain profile. Something like this is possible by strain engineering. So stay tuned. Now, before we go into what strain and how we do it, what strain does and how to engineer such a state, let's do a quick one-slide summary of graphene electronics. So electrons, so graphene is formed when carbon atoms set themselves in a hexagonal lattice. And if you look at, so if you stare at this lattice for a while, you will realize that not every atom is equivalent. If you sit in an A atom, you will see bonds at 10 o'clock, 2 o'clock, and 6 o'clock directions. Whereas if you sit on the B atom, then the bonds are at 8 o'clock, 4 o'clock, and 12 o'clock directions. So there are two inequivalent atoms. The reciprocal calculate the band structure. It looks like this, with linear bands, linear dispersion near the Fermi at 0. If we take a line cut, like, and these, okay, so these bands are formed by the hybridization of the bonding and anti-bonding orbitals. And if we take a line cut like this, what we see is that there are the bonding and the anti-bonding orbitals cross each other at the corners of the Brillouin zone. And now this K and K prime points are like two inequivalent momentum points, just like there are two inequivalent lattice points in real space. There are two inequivalent momentum points in the reciprocal space. And so what we can imagine is that how electrons, so the unit cell of graphene has two atoms. So we can imagine that the wave function of graphene consists of two components of how electrons are delocalized between the two sublattices, A and B. Or equivalently, we can also imagine, also describe it as how electrons are described in the two valleys, K and K prime. So this can be thought of, this two component wave function can be thought of as a spin, which is a new degree of freedom that we can now manipulate. So how does strain manipulate this? So imagine an unstrained graphene lattice, which looks like just like a hexagon, unstrained graphene lattice in the reciprocal space. If we strain it, now what happens? The hexagon distorts. And of course, it is blown up. I mean, it wouldn't distort this much, but for the sake of seeing it clearly, we distort it too much. Now, when it distorts, you can see that the K point has gone to K plus delta K. But because of the symmetry of the problem, the K prime point, which is like minus K, goes to minus K minus delta K. If this moves by delta K, this moves by minus delta K. Now, if you remember our quantum mechanics course, we can write it in a very suggestive way. This delta K, we can write it as some PA over C, and then this minus delta K becomes negative of that. And this can be thought of as the emergence of a vector potential. So this is like generating a pseudomagnetic field, which is opposite signs. So unlike other real magnetic fields, which affect all electrons equally, in this case, this magnetic field would affect K and K prime electrons differently. So K electrons see a magnetic field of plus 10 Tesla, K prime electrons would see a magnetic field of minus 10 Tesla. And some very smart people before us, about a decade back, or maybe even earlier, figured out that the vector potential is proportional to the strain. Not only can we generate a pseudo-vector potential, we can also generate a pseudo-scalar potential. So imagine now, let's go to real space, and you have a lattice here. And imagine that it blows up under strain, or it gets contracted. What happens as it changes its size? The density of ions change inside this region. As the density of ions change, so does the density of electrons, because it has to be charge neutral locally. Now, as the local density of electrons change, the local potential, the V voltage potential, local scalar potential, that which is proportional to charge of electron times density of electrons, that also changes. So this is like a scalar potential. So then this can be used to generate electric fields. And again, some very smart people showed us the way that a pseudoscalar potential can also be generated, how it is related to strain. Now you might imagine that, okay, big deal. Whoa, I mean, it was charge neutral initially, it was charge neutral later. So what did change? And you'd be right, nothing really changes. Nothing really changes if you have uniform strain. What you really need is gradient of strain, because the potentials are proportional to the strain. So, but potentials are, you cannot measure them directly. They're non-physical. What you can measure are the fields, and the fields are the derivatives of the strain, derivatives of the potential. So what you need is derivative of strain. So people would often say that strain creates pseudomagnetic fields. What they really mean is strain gradients create pseudomagnetic fields. And make no mistake that these fields are actually as real in detection as actual fields. So for example, if we take a 2D lattice like graphene and apply an external magnetic field, then the electrons start going around in circles, forming quantized levels like Landau levels, called Landau levels. And for Landau levels, for Dirac electrons, the energy of the nth state is proportional to square root of n. And this is in parallel. There is no magnetic field here. What they have done is they have put nano bubbles of graphene. They've grown graphene, and then thermally contracted the substrate. So as the substrate contracts, then graphene sort of buckles out. So these are these bubbles. And if you measure do DIDV measurements on these bubbles, what you find is there are peaks in the spectra, and they are En proportional to square root n, just as you expect. So these pseudomagnetic fields, they are as real as they can be detected as really as actual fields. Now let's see at what happens in our case. So we have periodically rippled graphene. So first thing we do is that we take a spectra far away from the rippled graphene, so that we know what is happening. If you take a spectra here that is shown here, which is the V shape, as you would expect for normal graphene. If we take a spectra here on the rippled region, a series of peaks appear in the DIDV. So, and they are equally spaced. And if you want to know what is the effect of only strain, we do B minus A, which is the effect of here minus this spectra taken here minus here, this minus this, which is red. So it flattens out, loses its V shape a lot, and there are a series of peaks. If we plot the nth peak, energy of the nth peak versus n, we see that they fall into a beautiful straight line. So this is in contrast to what they had here. En was proportional to square root n. Whereas here what we are seeing, E is proportional to n. This is just like a harmonic oscillator. So what is happening? Okay, so we scratched our head a little bit. And then we said that, okay, let's make sure that we're not doing something stupid. So we started taking a spectra along a line. So we climbed up the step edge, and at each point here, different points, we stop and take a spectra. And then from each spectra, we do the same thing. We subtract out what is the average graphene spectra so that we keep only the effect of strain. And this is what we find. So we stop along 27 points. This is the Z height. So this is the bottom terrace, this is the top terrace, and this is how the height is increasing. Spectra taken on the flat terraces, after we subtract the average, they sort of flatten out. That means they're just like graphene. There's no strain, nothing new happening. On the top, at the bottom. Only on the draped region, which is like point around 8th to 19th, these peaks appear. So this is clearly an effect of strain. But what does this mean? So then what we do is that we take a series of spectra parallel to the step edge. We stop along 100 points, and at each point we take 100 spectra, 150 spectra. And what we see is that the amplitude of these DIDV measurements, the amplitude of these peaks go up at the kinks. So that is, if you're sitting on a crest or a trough of a ripple, it has higher amplitude. They're more prominent there. So this was the first hint that we are seeing something that has to do with strain. So this is the Z height as we travel along here. And this is on in red, I show the amplitude of these peaks. So every time there is a kink, there's a crest or a trough, there is a peak in the DID measurement. So that means in those points, these peaks are more prominent. Okay, so that's the measurement. And at this point, we ran off to our theory colleagues and we told them, we don't know what we're seeing, please help us. And so they started simulating rippled graphene. And you can imagine that if you have a piece of cloth that is bending, there are two ways it can deform. One is, of course, the out-of-plane deformation, how much it buckles out. The other is an in-plane deformation induced by the curvature. So if it bends like this, there is an in-plane curvature. So, and when you calculate what is happening in graphene, the density of states, how density of states change in graphene, they find out, surprisingly, that yeah, there are equally spaced peaks. However, if you consider only the out-of-plane bending, then the higher magnitude of the density of states occurs at the peaks, at the middle, not at the peaks. So, but this is not what we are seeing. Low density of states at the peaks. So this is not what we are seeing. However, if they consider both out-of-plane bending and in-plane stretching, then higher density of states happen at the peaks. So this is how graphene bends. There's not only out-of-plane bending, but there's also curvature-induced stretching. So this is how an atomically thin sheet bends. Okay, so this is our right model. And now what, based on this, is happening? So as graphene ripples, there is a strain at different regions varies. So there's a strain modulation. As the strain gets modulated, different regions have different CC, length of the CC bonds. So at the crests and troughs, the graphene gets stretched out, and so there are large carbon-carbon bonds. And if we, in the flat regions on the edge, on the surface, flat regions between the crests and troughs, in those regions the graphene doesn't stretch out as much. So comparatively, there are smaller carbon-carbon bonds. Now, if you remember what we talked about earlier, that there was strain, it's not strain that creates pseudo gauge fields, it is strain gradient. So at the boundary of these two regions, like in the here in the first picture, the whitish region, in those regions there are pseudo electrical magnetic fields arise. So in blue and red are the pseudo magnetic fields which are in Z out of plane direction, and in pink I show the electric fields which are in plane. So this is a simple picture, but our theory colleagues also did rigorous calculations, first principle calculations. So here what I'm showing in the X direction is the energy. In the Y direction, this is the traveling along the ripple. So, and they see that there are actually equally spaced peaks as we have seen in our spectrum. And so this is the density of states of graphene lattice under periodic strain, like here. In here, they don't put the periodic strain, but instead they put a electric and magnetic field profile like this. And it also creates the equally spaced electric and magnetic fields. And the effective magnetic fields that they see can be as high as 200 Tesla. Now, generally what you have is like the highest DC field that you can create is of the order of 100 Tesla or something. This is higher than that. So this, you can imagine, this is like taking an MRI machine, which is the size of a room, shrinking it down to 10 nanometers and making it 100 times stronger. That's what we have done. Now, what this means is what is happening in this case is this. So we are creating a superlattice of electric and magnetic fields. Generally, when people create superlattices, what they do is that they interface different materials with each other. And at the interface, where the electrons are subjected to potentials from different materials, the electrons have some interesting electronic properties. So this is one example of stacked superlattice, an oxide superlattice. Or similarly, here is a lateral heterostructure where two materials, A and B, whatever, they can be anything. And at the interface, something interesting happens. In our case, what we are doing, it's a completely new way of creating a superlattice. What we are showing is that if you have a material which is strong enough, like graphene is, you can periodically modulate the strain. As you periodically modulate the strain, some parts of the lattice become stretched out, some parts of the lattice become squished in. So it is like dense and rare. And these dense and rare regions are in some sense different materials. At the edge of these different materials, just like at the edge of these different materials, you can have electronic states. At the edge of these different, quote unquote, different materials, since the material is graphene, you can create, the electrons can be described by a very simple, elegant method of pseudoelectric and magnetic fields. The entire description boils down to something very simple. So this is so here we have interfaces, superlattices created by different materials. We create a superlattice of the same material modulated by strain. So this is a totally new way of creating a superlattice. So we name these strained electromagnetic modulated superlattice, or streams for short. Finally, an implication or an outlook of what this means. So if you have in a region a very non-uniform magnetic field, so here it is pointing out, here is pointing in, an electron would go like a snake step. It will just be, so because in this region it bends in one way, and this region it bends the other way. So it will move like a snake step, like a snake. And secondly, it cannot move the other way. It has to move. If it's moving down, it has to keep moving down. It cannot move up. Here we have the exact same thing. We have interface of magnetic fields, pseudomagnetic fields, and the electrons, they must move in one direction. But this is not a real magnetic field. It's a pseudomagnetic field. And so K and K prime electrons see opposite magnetic fields. So that means if K electrons can travel up the ripple, then K prime electrons can only travel down the ripple. So it cannot travel the other. Now, these kind of things have been proposed earlier. So here is one PRL a couple of years back, where they proposed it by a nanobubble, but this has never been realized before now. And so you can imagine that there are these counter-propagating states of K and K prime momenta which are traveling in opposite directions. So this is exactly like a topological insulator, where opposite spins travel in opposite directions. But there is no topology here, or you can describe probably in terms of topology, but this was achieved just by strain engineering. No spin orbit coupling or anything. Okay, I think I'm out of time, so let me summarize quickly. So we developed a technique to study mechanical and electronic properties of nanoscale ripples in suspended graphene. And then we found that there are two conserved angles, draping and rippling angle, which means that if you take graphene, it behaves like a bizarre fabric, which can only buckle in a certain way, no matter how you try. Then we demonstrated that there was a possible breakdown of continuum elasticity theory. And we found spectral signatures of strong non-uniform pseudo gauge fields. And we also demonstrate a strain electromagnetic modulated superlattice, streams for short. Finally, I would like to thank all my collaborators here at Penn State and the theorists in Belgium, and all of you for taking the trouble to come and listen to my talk, especially on a snowy and frosty day like this. Thank you.
Thank you, Riju. While we wait for questions online, maybe we could have some questions in the room.
Let me start. So this material, what's the grain size of this graphene?
Grain size, it's so we have imaged like size of microns-ish, and I haven't seen grains.
So you assume this is a monocrystalline?
Yes, it's a monolayer. And also because, yeah, it's a monolayer.
Monolayer is a different issue.
Yeah, monolayer is a different issue.
Monocrystalline.
Monocrystalline.
You mentioned continuous material versus discrete lattice. Can you explain the difference?
Oh, so if you have a piece of cloth and you stretch it like this, okay, so, oops, if you stretch it like this, then the wavelength of the ripples that form, that is much larger than the individual thread size of the cloth, right? Or if you take a plastic sheet, then the atomic scale is much smaller. Okay, so at the length scale over which the strain varies, that is much larger than the discreteness of the in material. So you can safely take it as a continuous material. Okay. But in this case, if you make the strain length scale of strain variation smaller and smaller, at some point it is not going to be a continuous material anymore. It's going to see the discreteness. So at some point, that classical theory should break down, and it demonstrates it does.
Why was the En versus N is supposed to be linear?
Yes.
And what is N there?
N is the index of the peak. Just like a harmonic oscillator, N equal to 0, 1, 2, 3.
And there's a theory prediction about the nanodomains
Yes.
versus En versus
Yeah, so, yeah, I think I get what you're saying. So, just hold on a second. So, you wanted, so the, okay. So what is really happening here? What is happening is these small regions here, they create their own magnetic field. And these magnetic field create their own Landau levels, which are going around. Now, since the de Broglie wavelength of the electrons in a semi-classical theory, it is sufficiently large if we calculate it. So the electrons interact with all these Landau levels. So all these Landau levels interact with each other. And out of that comes out E proportional to S. Why that is, here is a simple picture. So imagine you have, imagine let's say that the magnetic fields I approximate by a series of delta functions. Okay, simple model. If I model them as a series of delta functions, then the vector potential A is like a theta function. And now this is problem then now reduces to solving chronic penny model for Dirac electrons. And so this is a simpler problem, like if you have a graduate course homework problem. Homework problem can be like this. And you can solve this. It's not very hard to show that this will give you n proportion to n. So other people saw Mike-Cromie, these people saw E proportional to square root n because this is a uniform magnetic field. In our case, it's highly non-uniform, and that creates the difference.
How much strain can you apply to graphene before crack propagation begins as defect?
I think it's about 20%. About 20% is the number. Yeah, people have actually, so what they have done is they've taken a graphene sheet and then punctured a hole with the AFM tip. And in measuring how much force you need, they can calculate it's like about 20%.
Well, that's pristine then, right?
That's pristine.
Once you have a defect there,
then
how
it's
much
not.
can you pull
Then,
before?
yeah, I know. Yeah, but certainly it will go down, but at least for the 10%, this was pristine graphene.
So those like special conserved angles in the rippling, were you able to relate those back to some fundamental property of the graphene? Why is it those?
So possibly. So one thing is this angle. This is the draping angle. The draping angle is conserved because we think this has something to do with what is the force, like how hard copper is pulling on the graphene. As the van der Waals force of the copper and the graphene is conserved, that has something to do with this angle being conserved. We think. And for the rippling angle, I really have no idea. However, I'll say this, that this is a really rare occurrence in experiments where you need two things. One is it has to be suspended, which is you can imagine that if you have a piece of cloth and you're taking it down at arbitrary distances, like if there is a substrate underneath it, then it's not really free to bend the way it wants to. So what you need is it has to be suspended, and secondly, it has to be sufficiently small so that it's away from the classical regime. And those two are a very rare occurrence in experiments. So other than our experiment, I found another paper where they actually imaged this kind of, I think I have it here somewhere. So in that paper, yeah, so what these people did was that they bombarded ions on a copper substrate and they dug trenches. And on these trenches, they started growing graphene. So the graphene also got, but all of their trenches were about the same size. They couldn't vary it by an order of magnitude like the way we did. But if you measure the rippling angle here, it is the exact same angle that we find. So 2 experiments halfway across the world, 5 years apart, reproducing the exact same angle. That means it is correct. But I don't have an idea. And I'll say that people who are much smarter than me have thought that they also don't have an idea. Yes.
We have a question online. How might one actually use these localized ribbons of pseudospin in a device?
That is a great question. So how you might use them. So one thing is if you can do this for a long enough, if you can have this for a long enough ribbon, then you can create a valley filter where only k momentums travel in one direction, k prime momentum travels in another direction. So that's like a valley filter, and that's like a topological insulator because they cannot scatter back.
I think their concern was making a contact with the small ripples. Yeah, what do you think about that? How do you?
That's a really hard problem. I don't know. Yeah.
They suspected it was too, but they didn't know if you had any insight.
No, I don't. It's more of a, in principle, demonstration of phenomena. Principle.
Do you know the copper orientation underneath graphene?
It's 111.
The temperature.
Here it's 111.
You try with other orientation?
No, I haven't.
Because
Yeah, that's an interesting thing to try.
The angle may differ too.
Yes, because the angle, at least the draping angle, should be different.
Any idea about the N and P asymmetry? I saw that the N channel has different arm and also it doesn't show any oscillations.
Oh, yeah, that's right. So we talked about this with the theorists, and their thing is it comes from doping from the copper. So the copper dopes it in asymmetry.
So I was wondering, as you pull on it, you make a K and K prime points move out, but you're also breaking you have 3 similar K points
Right.
coming in. Is that also?
I think that is also symmetric. The way they move, that's also symmetric.
I see. So the effective.
Yeah, the effective
field
field
of those.
is.
Any more questions on site? If not, let's thank Mr. Riju Banerjee one more time.